Hello and welcome to today's lesson where we're going to look at Coulomb's law in the electrical fields module of AQA A-Level Physics. So in today's lesson what we're going to do is we're going to look at an introduction to electrical fields and try and describe an electrical field. So if we're successful and we learn in today's lesson, we can define what an electric field is and state its importance to nature, describe the force experienced on charged objects in an electrical field, and calculate the force experienced on charged objects in an electrical field, which links into the following part of the AQA A-Level Physics specification. So a field is an important concept to define in the universe. A field is a region in the universe where an object placed inside of it can experience a non-contact force due to its position in the field. So the properties of the field are given by the virtual particles of the force interaction. So objects must contain a certain property to experience a non-contact force inside the field. So in gravitational fields this property is mass. In electrical fields this property is charge. Now if an object has no charge it experiences no force inside of an electrical field. Now, so we previously considered gravitational fields. So in gravitational fields we know that it acts on objects with mass, it extends to infinity, it exerts weak forces, and it's always attractive. Now as we move through this topic we can contrast electrical fields with gravitational fields. So electrical fields act on objects with charge, they also extend to infinity, they exert strong forces, and they can be attractive or repulsive. Now, any field in physics can be described with four main properties, and the definitions of these properties is consistent amongst all fields. So learning these definitions is integral to understanding the physics of any field. So the first property is the force law, which is what we're going to cover in today's lesson. This details the force exerted between two objects inside the field, and it's usually named after the famous scientist who worked in this particular field of physics. Now, the second property is the field strength. This details the force exerted on one object per unit property of the field due to the object being in that field, and this is due to the field produced in the universe. So for example, the gravitational field strength is the force per unit mass experienced by an object inside a gravitational field. The third property is potential. This details the energy stored in one object per unit property of the field due to the object being in the field, and again it's due to the field produced in the universe. So the gravitational potential is the energy per unit mass experienced by an object inside a gravitational field. And property 4 is the potential difference. This details the work done moving an object per unit property of the field from one point in the field to another point in the field. So for example, the gravitational potential difference is the work done per unit mass experienced by an object moving from one point in the field to another point in the field. Now the absolute potential difference details the work done moving an object per unit property of the field from outside the field, which we define as infinity, to a point in the field. So the absolute gravitational potential difference is the work done per unit mass experienced by moving an object from outside the field to a point in the field. Now, remembering these key definitions is crucial to the understanding the physics behind any field. Now, you can look at several demonstrations, including the idea of magnets levitating, the idea of a paperclip being attracted to a magnet, and it shows you that objects do not have to be touching to exert a force on each other. So here, the electrical or magnetic force of repulsion is being exerted, yet the objects are not touching. Now, this means objects do not have to be touching to exert a force on each other. So the gravitational force, the electrical force, the magnetic force, they are all examples of non-contact forces. So the Earth and the Sun are not touching, yet there's a gravitational force between them, so gravitation is a non-contact force. However, some forces do need objects to be in contact with each other to exist, which we call contact forces. So the example of friction, when a ball and a surface rub against each other, which prevents smooth movement, the idea of the reaction force being provided by a surface to stop an object falling through it, the idea of tension being caused by an object pulling on another object to stretch it out. These are all examples of contact forces. So all forces between objects are either contact, where the forces are produced when the objects are physically touching, or they can be non-contact forces, which are forces produced when objects can be physically separated. Now, objects can exert non-contact forces by transmitting a field in space, and a field is a region of space where a body can feel a force. So, for example, the Earth's gravitational field is the region of space where you can experience the Earth's gravitational force, and these are represented by field lines. So, examples of fields in physics include gravitational fields, and they include magnetic fields, as shown in these particular diagrams. Now, we visualise the effect of an electrical field with field lines. Now, these are drawn as straight lines from the object with arrows on them showing their direction. Now, any charged object inside the electrical field of a particle will feel the electrical force. The objects do not have to be touching. Now, the electron in this example will produce an electrostatic field or electrical field because it has a negative or any charge. Now, it's important to note that the electrical field lines cannot overlap each other in diagrams. Different electrically charged objects can have interacting field lines, but they cannot overlap. Field lines from charged objects can join up but cannot cross. Now, this is because the field lines show the movement of a unit positive charge in the field if it was placed at that point. So, electrical field lines always show the path a positively charged particle would take if it was placed at this point. So, in this example, the positively charged particle would move towards the negative electron because negative and positive would attract each other, so the field lines are pointing inwards. Now, this is important that all electrical field notations always consider the impact to a positive charge. Now, there's no fundamental principle behind this rule. A positive charge is used to standardize all equations regardless of context. So remember, for negatively charged objects, the field lines will be pointed towards that particular object, whilst for positively charged particles, the field lines will be pointing away, because a positively charged particle placed near another positively charged particle would cause a repulsion, so it would move away from it. So the field lines point away from the object, which is very, very important. Now, how close the electrical field lines are together, or the density of the field lines, shows how strong the electrical force is. The denser the field lines, the stronger the force exerted. So where the field lines are more spread out, the force experienced will be weaker. Where the field lines are closer together, the force experienced will be stronger. So an electrical field, which is a region around a charged particle within a non-contact force will be exerted on other charged particles, is represented by field lines, and the field lines show the path a positively charged object on that line would take, whilst the density of the field lines shows the strength of that electrostatic force. So you've got to be able to draw electrical field lines accurately and not make mistakes in these diagrams. So the interactions of the field lines in electrical fields can produce many complex patterns such as the following, which we can see in these following animations. Okay, and it's better to show electrical field lines as an animation, as it shows the path taken by a unit positive charge in an electrical field. So you can see it in all these different examples. Now, you need to be able to show the motion of charged particles in an electrical field line with the field line shown, which is very important. However, individual particles, which we assume any charged object to be, can produce fields of two different shapes. So what's the difference in the electrical field line shapes, and when is each field produced? Well, you've got something called a radial field and something called a uniform field. Now, a radial field can be produced by any particle, whilst a uniform field is produced by parallel metal plates, such as a capacitor. Now, in a radial field, the electrical field lines point in the direction a positive charge would take, and it's the same example in a uniform field. Now, in a radial field, the electrical field strength decreases with distance in the field as the field lines spread out, but in a uniform field, the electrical field strength is constant throughout the field because the density of the field lines remains constant. Now, in today's lesson, we're going to focus on radial fields, and we'll look at uniform fields in the next lesson. Now remember, the field lines indicate the movement of a positively charged object placed in the field. So we're going to examine the forces generated between two charged objects in electrical fields. Now, our understanding of electrical fields took a long time to develop. So ancient cultures around the Mediterranean knew that certain objects like amber could be rubbed with cat's fur to attract light objects like feathers, and this allowed us to make observations regarding static electricity. Then in the 18th century it was suspected that the electrical force diminished with distance as the force of gravity did, and people like Volta and Bernoulli thought this to be the case. And then based on experiments with electrically charged spheres, Joseph Priestley was one of the first to propose the electrical force followed the inverse square law, similar to Newton's law of universal gravitation. And so based on experiments with electrically charged spheres, we looked at this inverse square law, which is similar to Newton's law of gravitation. Now, both gravitational fields and electrical fields follow the inverse square law when considering the force produced between two objects. This occurs as both gravitational fields and electrical fields work by the same underlying mechanism. Now, both field lines spread out as spheres, which gives us a 1 over r squared due to the surface area formula of a sphere. So, what will happen is that whilst your electrical charge will produce a spherical electrical field, the greater the distance from the electrical charge, the larger the spherical electrical field. So the greater the distance from the electrical charge, the larger that spherical electrical field. So it indicates that the field lines are spread out over a greater area now, decreasing the actual electrical field strength because those field lines are more spread out. Now remember, it's spread out as a sphere, and that's given by the equation 4 pi r squared, which gives us the inverse square relation. So we found that actually that there was similarities between gravitational and electrical fields. However, there was two major differences. The field strength of each field, so we had to represent the different fields with different constants. And electrical fields can be represented, but can either be attractive or repulsive, which is represented by plus or minus, whilst the gravitational field can only ever be attractive. Now in 1785, the French physicist Coulomb published his first of 3 reports on electricity and magnetism, where he stated the mathematical relationship between the electrical force and the distance between the objects, which he called Coulomb's law. So this is a very important law to learn in physics. Now Coulomb measured the electrostatic force between two electrical charges, and he defined opposite charges, the attractive force, to give a negative value for the electrostatic force. So this occurs because positive times by negative is equal to a negative. Now note, when we measure the separation between the two charges, we take it from the centers of mass, not from the surfaces of the objects. So it's from one center of mass to another center of mass. Now we also defined same charges producing repulsive force as a positive value for the electrostatic force, because positive times by positive is equal to a positive, and negative times by negative is equal to a positive. So he concluded from his experiments the following ideas on the electrostatic force. That firstly, that the electrostatic force is proportional to the products of the two charges that produce this electrostatic force, and it's inversely proportional to the square of the distance between them, which forms our basis of Coulomb's law. So the relationship between the electrostatic force between two charged objects and the separation of the two charged objects is F is equal to 1 over r squared. So when the separation is doubled, the force exerted decreases by a factor of 4 because it's 2 squared. Now, you've got to be able to state the relationship of Coulomb's law as well as the mathematical equation. So our mathematical equation links into F is directly proportional to Q1 times by Q2, the products of the charges, divided by r squared, the square of the separation between those two charges. But if it's directly proportional, there must be a constant in there. And the constant is linked to what we call the permittivity of free space. So it is equal to 1 over 4 pi epsilon 0, where epsilon 0 is the permittivity of free space, which is 8.85 times 10 to the minus 12 Coulomb squared newtons to the minus 1 meters to the minus 2. Now, this is very important because this value can change depending on the material between the charged objects, but at A level we always assume that there's air or a vacuum between the objects. So we can actually state Coulomb's law as the following. F is equal to 1 over 4 pi epsilon 0, the permittivity of free space, times by Q1 times by Q2 over r squared, or we can say F is equal to Q1 Q2 over 4 pi epsilon 0 r squared. So this equation calculates the electrostatic force between two objects due to the electrical fields, and both charged objects will experience this force. So this force is the same force on each charge. However, The charge is used instead of mass in the equation because it's very similar to the Newton's law of gravitation, but instead of it being the mass in the equation, it is in fact the charge that's being used. Again, it's very similar to the gravitational force equation, but there's a much larger constant being used in the equation because the electrical force is a much larger value than the gravitational force. And for Coulomb's law to be accurate, 3 assumptions are made. Assumption 1, objects in this particular example are considered point charges. Assumption 2, the charged objects are not touching. And assumption 3, the charged objects must be stationary. Now, like we said before, this equation is very similar to Newton's law of gravitation as they both explain the force generated in a field. So they actually have a very close relationship in the sense of they have the same format, except there's not masses being used in Coulomb's equation, it is charges, and it's not the universal gravitational constant, it's 1 over 4 pi epsilon 0. So let's look at an example calculation using Coulomb's law equation. So it could be find the force experienced by a free electron 2.83 millimeters from the center of a 1 millimeter sphere carrying a charge of plus 0.510 microcoulombs. The charge of an electron is minus 1.60 times 10 to the minus 19 coulombs, and the mass of an electron is 9.11 times 10 to the minus 31 kilograms. So the first thing you would do is identify that the force given between two charged objects is calculated with Coulomb's law. You then pop in the values from your equation, make a note of the fact that we have prefixes in there in terms of milli and micro. We then remember that the separation is from the center of the masses, not the surfaces of the object. We then place the values into the Coulomb's law equation. We calculate the force exerted. Now always remember that R value is squared. People commonly forget to do this in questions. So our value is force is equal to minus 9.16 times 10 to the minus 11 newtons. Now remember to give your answer to the correct number of significant figures with the correct units and state whether the force experienced by the object is either an attractive force or a repulsive force. Now remember, a negative value shows the charges are attracting each other because one is a positive and one is a negative, so when multiplied that will equal a negative value. So this negative value shows the two charges must be attracting each other. So just remember, give your value with the correct number of significant figures and don't forget to square your separation value. It's a common mistake made in questions. And remember that both the free electron and the sphere in this particular example experience this particular charge, and you can state if the force between the objects is an attractive or repulsive one by looking at the sign of the value. So let's just look at the key points. An electrical field is a region in the universe where a charged object will experience a force when placed inside that field. The field lines of an electrical field indicate the movement a positively charged object would make if it was placed in that position in the field. There are two main types of electrical field, radial and uniform. Coulomb's law indicates the force generated between two charged objects within inside an electrical field, where Q1 times by Q2 over 4 pi epsilon 0 r squared is equal to that electrostatic force, which is experienced by both charged objects in the example. And Coulomb's law indicates that the force generated between two charged objects is directly proportional to the products of the two charges, yet inversely proportional to the square of the separation between the objects. So if we've learned in today's lesson, we can state the force between point charges in a vacuum. We can link it into the permittivity of free space. We have an appreciation that air can be treated as a vacuum when calculating the force between charges, and that for a charged sphere, the charge may be considered at the center, and we can compare the magnitudes of the gravitational and electrostatic forces between subatomic particles, and we can estimate the magnitude of those particular forces. So if we're being successful and we've learned in today's lesson, we can define what an electrical field is and state its importance to nature, describe a force experienced on charged objects in an electrical field, and calculate the force experienced on a charged object in an electrical field. Hope you've enjoyed today's lesson on Coulomb's law in the electrical fields module, and have a lovely day.